Long before telescopes, ancient astronomers mapped the heavens with astonishing precision. This is the world of ancient sky records, where early civilizations documented celestial phenomena that still shape our science today. By the end of this exploration, you will understand how these early observations form the very bedrock of modern astronomy. We will investigate why a supernova explosion was meticulously recorded in Imperial China and how Babylonian priests could predict lunar eclipses with remarkable accuracy. What does our own search for cosmic truth share with these star watchers from the distant past? The human story with the stars begins not in grand observatories, but in the open fields and silent nights of our deepest past. For the earliest societies, the sky was not a distant curiosity. It was a living clock and calendar etched in light. Their survival depended on reading its signs, knowing when the seasons would turn for planting and when the herds would migrate. This primal connection wove the cosmos directly into the fabric of their daily lives and spiritual beliefs. Long before the first written word, communities were building monuments that served as permanent sky watchers. Take the great stone circles like Stonehenge, for example. As experts like archaeoastronomer Clive Ruggles have shown, these massive structures were precisely aligned with the rising and setting sun at the solstices. A community did not move stones weighing tons on a whim. This was a deliberate, generations-long project to capture the rhythm of the heavens. They were encoding celestial knowledge directly into the landscape itself, creating a fixed reference point for the turning of the year. This was a practical science born from necessity, guiding agriculture and marking sacred times, but it was also the birth of a deeper inquiry. From simply tracking the sun and moon, these early astronomers began to notice more complex events, the sudden appearance of a strange star or the slow, wandering paths of planets against the fixed constellations. These phenomena demanded explanation and were woven into the myths and stories that defined their cultures. This foundational period, where survival and spirituality were one, set the stage for everything that followed. It was the crucial first step from simply observing patterns to beginning to systematically record them, a journey that would soon lead to the birth of true astronomy in the river valleys of Mesopotamia. From the silent stone circles, the story of sky watching moves to the bustling, river-fed cities of Mesopotamia. Here, on the fertile plains between the Tigris and Euphrates, scribes began to press styluses into wet clay, creating the first detailed celestial archives the world had ever known. These tablets, some dating back over 3,500 years, transformed starlight into permanent record. The most famous of these, the Venus tablet of Amasajuka, charts the appearances and disappearances of the planet Venus with meticulous care across a 21-year cycle. But these were more than just scientific logs. They were divine messages. The Babylonians saw the cosmos as a vast, readable text where the gods communicated their will. The steady rhythm of a planet's path might signal stability, while a surprise like a comet was a dire omen, a long-haired star portending upheaval for a king or the fate of an entire kingdom. This pursuit of celestial meaning was not guesswork. It was supported by a highly organized, temple-centered system of observation. Priests, who acted as the first professional astronomers, maintained detailed astronomical diaries in cuneiform script. They tracked everything from the moon's phases to the positions of planets, creating a vast data set gathered over centuries. This long-term commitment allowed them to discern profound cyclical patterns in the chaos of the sky. As scholar Francesca Rochberg highlights, they developed sophisticated mathematical models, enabling them to predict lunar eclipses with remarkable accuracy. They understood the Saros cycle, the repeating pattern every 18 years that brings eclipses back around. This was a science born from a belief that the divine operated with mathematical regularity. Our own search for objective truth might seem a world away from interpreting a comet as a heavenly warning, yet the Mesopotamian approach forces us to ask a profound question. Is any science ever entirely free from the culture that births it? Their blend of precise observation and cultural interpretation was not a contradiction. It was the very engine of their discovery. The desire to understand the gods drove them to measure the heavens with a precision that would not be surpassed for millennia. This powerful fusion of belief and calculation, archived on countless clay tablets, would become a priceless inheritance, its ideas flowing down the trade routes to influence the star watchers of ancient Egypt and far beyond. Across the desert, the Egyptians raised their own stone prayers to the stars, engineering a perfect alignment between heaven and earth. Their civilization was built on the rhythm of the Nile, and they saw the cosmos as a divine map for that life-giving cycle. The annual flooding of the river was their most crucial event, and they linked it directly to a celestial herald, the star Sirius. Egyptologist Juan Antonio Belmont notes that just before dawn each year, Sirius would reappear in the eastern sky after a long absence. This heliacal rising signaled the coming floodwaters, an event so vital it marked the beginning of their new year. Priests tracked this and other stars with incredible accuracy using simple but effective tools like the Merkit, a sighting instrument that let them plot the paths of the gods across the night. This was not abstract science, it was a sacred duty that sustained the kingdom. This celestial knowledge was carved into the very bones of their world. The Great Pyramid of Giza is a masterpiece of astronomical engineering, aligned to true north with a precision that seems impossible for its time. Its air shafts point directly toward stars like those in the constellation of Orion, which the Egyptians associated with Osiris, the god of rebirth. They were building a machine for the soul's journey, a ramp to the stars that mirrored their belief in cosmic order. The sky was not just observed, it was architecturally embodied. Inside tombs, the ceiling was often painted with star charts and the image of the sky goddess Nut, who swallowed the sun each evening and gave birth to it each morning. They even developed a system of 36 star groups called decans, which rose consecutively throughout the night and provided a reliable clock for the darkest hours. This deep connection filtered into daily life through documents like the Cairo calendar, which marked certain days as favorable or unfavorable based on the positions of planets and stars. A pharaoh's power was seen as divinely ordained by these celestial patterns, and the entire agricultural and religious calendar was governed by the sky. The Egyptian drive to harmonize human existence with the cosmos resulted in a seamless blend of myth, measurement, and monumental construction. It reveals a universal human yearning to find our place within a grand, orderly universe. This sophisticated integration of astronomy into every facet of culture created a legacy that would ripple eastward toward the observant scholars of ancient China. While the Egyptians built for eternity, a parallel tradition of celestial observation was flourishing on the other side of the world, one defined by its meticulous, state-sponsored record-keeping. In the imperial courts of ancient China, astronomy was not just a spiritual pursuit, it was a pillar of governance. A celestial event was never just a point of light. It was a direct message from heaven concerning the emperor's mandate to rule. This belief created one of history's most organized and continuous astronomical bureaucracies, where court astronomers held official positions with the grave responsibility of interpreting the sky's will. Their observations, etched onto oracle bones as early as the Shang Dynasty, and later compiled into texts like the Book of Documents, were so precise that they have become invaluable to modern scientists. For instance, their detailed record of a guest star in the year 1054, now known to be the supernova that created the Crab Nebula, provides a precise date that helps astronomers understand the life cycle of stars. This was not an isolated event. They systematically logged sunspots, eclipses, and comets, seeing them as signs of cosmic imbalance that could foretell hardship or a shift in dynastic power. To make these observations with the required accuracy, scholars like Xiaochun Sun explain how Chinese astronomers engineered remarkable instruments, such as elaborate bronze armillary spheres. These complex rings mapped the celestial sphere, allowing them to track star positions with stunning detail and create calendars essential for agriculture and imperial rituals. Their entire philosophical framework, rooted in the interplay of yin and yang and the five elements, was applied to the heavens. A comet's sudden appearance might be interpreted as an excess of yang energy, a disruptive force requiring a ceremonial response from the emperor to restore harmony. This seamless blend of cosmological belief and precise measurement raises a profound question for our own time. How much does our search for objective truth in the cosmos still depend on the cultural and political frameworks we build? The Chinese system shows us that the drive to understand the stars is often inextricably linked with the human need for order, both in the sky and on the ground. This legacy of state-sponsored observation, where every flash in the night sky was a potential political message, created an archive of cosmic events unmatched in its longevity. And as we will see, this human impulse to read the stars was not confined to the Eurasian continent, but was also rising independently under the vast skies of the Americas. Across the Pacific, Mesoamerican civilizations were engineering a relationship with the cosmos just as profound, yet uniquely their own. In the dense jungles and high plateaus, the Maya and Aztec peoples saw time not as a simple line, but as a sacred, interwoven fabric of celestial cycles. Their calendars were masterpieces of mathematical abstraction, designed to synchronize human events with the grand motions of the heavens. The Maya, in particular, developed the long count, a vast chronological system that measured time in cycles of thousands of years, while the Aztecs used the Tonalpohualli, a 260-day sacred calendar that intertwined with a solar calendar to create a 52-year cycle of renewal. These were not merely tools for marking days, they were frameworks for prophecy and ritual, dictating the most auspicious moments for everything from planting crops to waging war. This intricate knowledge was preserved in painted books known as codices. The Dresden Codex, one of the few surviving examples, contains incredibly precise astronomical tables. It charts the 584-day cycle of Venus with breathtaking accuracy, allowing Mayan priests to predict its appearances as both the morning and evening star generations in advance. They could also forecast solar eclipses, viewing them as moments of potential cosmic imbalance. This mathematical prowess was given physical form in their architecture. The Pyramid of El Castillo at Chichen Itza is a monumental solar calendar. At the equinoxes, the setting sun casts a series of triangular shadows down the staircase, creating the illusion of a giant feathered serpent, Kukulkan, slithering down to earth. This was more than a spectacle. It was a profound statement about the connection between the ruler, the people, and the cosmos. Specialized structures like the caracol, a round tower with strategically placed windows, served as observatories for tracking the path of Venus across the sky. The role of the priest astronomer was paramount. They scanned the night for omens, interpreting the sudden appearance of a comet or the erratic movement of a planet as messages from the gods. An Aztec legend tells of their patron deity, Huitzilopochtli, being born each morning as a warrior to battle the forces of darkness, a myth that directly linked the sun's daily journey to themes of sacrifice and renewal. This celestial knowledge was a direct source of political power. A Maya king might schedule his coronation to coincide with the first appearance of Venus as the evening star, thereby aligning his rule with the power of the heavens. It was believed that timing a military campaign with a specific planetary alignment could secure divine favor. This holistic system, which saw no separation between the movement of a planet, the success of a harvest, and the legitimacy of a king, forces us to reflect on our own modern relationship with time. Our precise atomic clocks keep us synchronized to the nanosecond, yet they are disconnected from any larger cosmic story. The Mesoamerican vision reminds us that time can be more than a measurement. It can be a narrative, a sacred cycle in which human life is deeply and meaningfully embedded. This drive to find order in the cosmos was also unfolding with unique philosophical depth in the ancient schools of the Indian subcontinent. In the ancient schools of India, the cosmos was understood as a single, breathing entity where science and spirit were one. Vedic texts like the Rig Veda contain hymns that are not merely prayers but profound astronomical observations, describing the sun as a wheel of eternal order and charting the paths of celestial bodies. This was the foundation of a system where the rhythm of the planets was inseparable from the rhythm of the soul. Later works, such as the Surya Siddhanta, took these poetic insights and forged them into precise mathematical models. It calculated the length of the solar year with an accuracy that would stand for centuries, and it detailed the causes of eclipses and the complex motions of the planets with a scientific rigor that feels startlingly modern. This knowledge was organized into practical frameworks for living. The nakshatras, or lunar mansions, divided the sky into 27 segments, each a resting place for the moon on its nightly journey. This system was far more than a star map. It was a celestial calendar that dictated the timing of rituals, agricultural cycles, and even the construction of temples, which were often aligned to specific star risings. The Jyotisha Vedanga, as scholar Subhash Kak has explored, provided clear rules for tracking solstices and equinoxes using simple instruments like the gnomon, a vertical rod that measured the sun's shadow to mark the passage of the year. These methods show a systematic, repeatable approach to observation that predated similar advances elsewhere. The great epics, like the Mahabharata, are woven with celestial lore, describing constellations and planetary conjunctions that scholars now believe may record actual astronomical events from a distant past. This entire system was framed by a grand vision of time itself. The concept of the yugas envisioned time as vast, repeating cycles of creation and dissolution, where celestial phenomena were not random accidents but part of a majestic cosmic order. Within this framework, even startling events found their place in myth. A solar eclipse was not merely the moon blocking the sun, it was the disembodied head of the shadow planet Ra who swallowing the solar disk, only for it to reappear moments later. Comets known as Ketu were seen as omens, their fiery tails interpreted as divine messages. This unique synthesis of narrative and calculation offered a complete worldview, one that found meaning in every flicker of the night sky. It challenges our modern separation of science and story, suggesting that the human drive to understand the heavens has always been about more than just data. It is a search for our role within an infinite, ordered whole. This profound desire to listen to the stars was not confined to the great civilizations of Europe and Asia, but echoed under the vast, open skies of indigenous cultures across the globe. Far from the grand observatories of empires, a different kind of astronomy was flourishing, woven into the very fabric of daily life and spoken memory. Indigenous cultures across the globe preserved a celestial wisdom that was both profoundly practical and deeply spiritual, passed down through generations in stories, songs, and stone. Without written texts, they became masters of oral tradition, where the night sky served as a living library and a sacred map. In Australia, Aboriginal Dreamtime stories do not simply describe the Milky Way. They are the Milky Way, a great celestial river connecting the land to the law of creation, with each dark dust cloud representing an ancestral being from a time beyond time. This knowledge was not abstract, it was a guide for survival, dictating when to find certain foods and how to navigate the vast outback. This pattern of embedding astronomy into culture is a global one. On the plains of North America, the Bighorn Medicine Wheel in Wyoming stands as a silent testament to this connection. Its 28 spokes, aligned with the summer solstice sunrise and the rising of key stars like Aldebaran, served as a ceremonial calendar and a physical anchor for celestial cycles. Anthropologist Von Del Chamberlain documented how the Pawnee people used star maps in their Earth lodges, with the position of certain stars signaling the seasonal migration of the buffalo herds. Their entire community's sustenance was coordinated by the heavens. Similarly, high in the Andes, the Inca carefully watched the star cluster known as the Pleiades. Its clarity and brightness upon its return to the night sky were directly correlated with the success of the coming potato harvest, guiding the precise timing for planting. This was astronomy in direct conversation with the ecosystem, a deep ecological connection where a shift in the stars could foretell a shift in the health of the land. This celestial knowledge was also a tool for epic exploration. The Polynesian voyagers are perhaps the ultimate example, navigating the trackless Pacific Ocean by reading a complex symphony of natural signs. They memorized the rising and setting points of hundreds of stars, watched the subtle patterns of ocean swells, and followed the paths of migratory birds. Their canoes were not just boats, they were moving observatories, and their mastery of wayfinding without instruments remains one of humanity's greatest navigational achievements. They encoded this wisdom in chants and stick charts, ensuring that the knowledge of the star paths would never be lost. Even dramatic celestial events were recorded. In what is now the American Southwest, a petroglyph at Choco Canyon is believed by some researchers to depict the supernova of 1054, the same event meticulously logged by Chinese astronomers. A single, spiraling symbol carved into rock captures a moment of cosmic violence that was witnessed and remembered across the world, proving that the impulse to document the heavens is a universal human trait. In an age of digital data and satellite GPS, what can these oral traditions teach us? They reveal that knowledge is not solely about precision, but about relationship. They show us diverse ways of knowing where the stars are not distant points of light, but active participants in a shared story of life, guidance, and memory. The elders who held this wisdom were living libraries, and their legacy challenges us to see the sky not just as an object to be studied, but as a presence to be understood. This global tapestry of observation brings us to a crucial point: to examine the specific, startling phenomena that captivated every one of these ancient cultures. A sudden streak of light with a long, ethereal tail would have been a terrifying sight in the ancient world. Across cultures, these hairy stars or broom stars, what we call comets, were universally seen as omens of profound change. Their unpredictable appearances broke the steady rhythm of the planets, sparking a potent mix of fear and fascination. In the imperial courts of Han Dynasty China, court astronomers did not just note a comet's presence, they meticulously documented its path, its color, and the direction its tail pointed in the official annals. This was critical intelligence, for a comet was a direct message concerning the emperor's mandate to rule, potentially foretelling a natural disaster, a shift in power, or the fall of a dynasty. The appearance of Halley's Comet in 1066, famously stitched into the Bayeux Tapestry, was interpreted across Europe as a divine sign foretelling William the Conqueror's victory at the Battle of Hastings. It was a celestial endorsement woven into the very fabric of history, yet interpretations varied dramatically. Greek philosophers like Aristotle believed comets were atmospheric phenomena, exhalations from the earth that burned in the upper air. Babylonian astrologers, by contrast, meticulously linked their appearances to the fates of kings and the stability of empires, seeing them as direct, if troubling, communications from the gods. This rich tapestry of ancient observation is not merely historical curiosity, it is active scientific data. Researchers like Donald Yeomans have combed through these old records, matching ancient descriptions to the orbits of known periodic comets. The value of this is staggering. Chinese records of Comet Halley, for instance, provide a continuous timeline of its appearances stretching back reliably to 240 BCE. This long-term data set is a gift to modern astronomy, allowing scientists to refine their orbital calculations and understand how a comet's path slowly changes over centuries due to gravitational nudges from planets. These ancient fears and fascinations, born from a confrontation with the unknown, now fuel our scientific understanding of these icy visitors from the solar system's edge. They teach us that our response to celestial mystery has always been to observe, record, and seek meaning, a drive that transforms superstition into science over generations. This human impulse to document the sky's most dramatic changes was tested again by an event far more violent and permanent than a passing comet: the sudden, brilliant appearance of a guest star. A brilliant new star, blazing where none had been seen before, was an event that shattered the celestial order. Ancient astronomers called them guest stars, and their sudden, silent appearance was both a marvel and a profound mystery. While a comet was a traveler passing through, a guest star was an uninvited resident, taking up a fixed position among the familiar constellations for months, sometimes even visible in broad daylight before slowly fading from view. The most famous of these was the star that appeared in the constellation of Taurus in the year 1054. Chinese court astronomers of the Song Dynasty, along with their counterparts in the Islamic world and likely artists in the American Southwest, all witnessed and recorded this astonishing event. Their descriptions are not vague myths, they are precise clinical reports. The official records from the Song court note that the star was visible in the daytime for 23 days, glowing with a reddish-white light, and that it remained observable in the night sky for a total of 652 nights. This was no atmospheric flicker, it was a cosmic cataclysm occurring 6,500 light-years away. The violent death of a star that we now know created the beautiful, tangled Crab Nebula. For the Imperial court, this guest star was a direct celestial omen, a sign that demanded interpretation and a potential challenge to the emperor's authority. Yet, in the Islamic world, a scholar like Ibn Batlan in Constantinople recorded the same event with a different focus, noting its position and brilliance as a pure astronomical phenomenon. This global network of observation, from Korean annals to European monastic chronicles, created a scattered but invaluable archive of stellar deaths. Modern astronomers like F. Richard Stephenson have become celestial detectives, cross-referencing these ancient positional data with the known remnants of supernova explosions seen through our telescopes. The Chinese record of the guest star's position in 1054 aligns perfectly with the expanding gas cloud of the Crab Nebula, allowing us to date its birth with an accuracy that would otherwise be impossible. This is the interdisciplinary power of ancient records. They provide the timestamp for cosmic events, helping us understand the life cycle of stars from their spectacular ends. The sheer brightness of these events cemented their place in human memory. The supernova of 1006, likely the brightest stellar event in recorded history, was described across China, Japan, the Middle East, and Europe. A Swiss monk noted it as a brilliant new star in the constellation of Lupus, astonishing and frightening. An Egyptian scholar, Ali ibn Ridwan, wrote that its light was a quarter that of the moon and it cast shadows on the ground at night. This global witness of a single point of light, a star that had detonated millennia before its light finally reached Earth, speaks to a shared human curiosity that transcended culture and creed. How do these ancient observations enhance our grasp of cosmic evolution? They provide the critical timeline, the historical context that transforms a beautiful nebula from a static photo into a dynamic, evolving story. They prove that the universe is not a fixed backdrop, but a living, changing entity where stars are born and die on time scales that, while vast, are now measurable because of these meticulous ancient notes. The next time you look up at a seemingly permanent constellation, remember that its peace is an illusion and that our ancestors were there to document the moments that peace was broken. This human drive to understand even the most predictable celestial events is perfectly illustrated by the cosmic clockwork of eclipses. A solar eclipse plunged the ancient world into an eerie, midday darkness, an event so unsettling it was seen as a dragon consuming the sun. Across civilizations, the predictable rhythm of the cosmos was suddenly broken, and the response was a fascinating blend of terror, ritual, and relentless observation. The Babylonians, masters of celestial mathematics, viewed these events through a lens of divine omens, yet their approach was anything but superstitious guesswork. They had identified the Saros cycle, a repeating pattern of approximately 18 years after which the Sun, Moon, and Earth returned to nearly the same alignment, bringing a similar eclipse. This allowed their priest astronomers to predict lunar eclipses with stunning accuracy, creating detailed astronomical diaries that noted not just the time and duration of an eclipse, but even the weather conditions and the planets visible in the darkened sky. This was data collection on a grand scale, driven by a belief that the gods communicated through mathematical regularity. As scholar John Steele emphasizes, these ancient eclipse records are not mere historical curiosities, they are active scientific tools. By comparing the recorded time and location of a Babylonian eclipse with our modern computer models, researchers can detect a tiny discrepancy. This gap reveals a profound truth. The Earth's rotation is gradually slowing down, lengthening our days by a fraction of a second each century. The fears of ancient astrologers have thus helped confirm a fundamental aspect of our planet's long-term behavior. In China, the celestial dragon required a ceremonial response. The emperor and his court would spring into action during a solar eclipse, beating drums and shooting arrows into the sky to frighten the beast away and restore the sun. This was a state-sponsored ritual to correct a cosmic imbalance, a direct threat to the emperor's mandate to rule. Yet, behind the ceremony was an equally rigorous tradition of record-keeping. Chinese annals provide consistently precise accounts, enabling modern astronomers to trace the slow evolution of the moon's orbit. This blend of myth and measurement was a global phenomenon. In Mesoamerica, a solar eclipse was a moment of profound fear, a time when the sun god might be dying, requiring human intervention to ensure its rebirth. Meanwhile, in ancient Greece, a different path emerged. The story of Thales of Miletus predicting an eclipse, whether legend or fact, marks a pivotal shift toward seeking natural rather than divine causes for celestial events. This universal drive to document eclipses had a profoundly practical side, anchoring human history itself to the clockwork of the heavens. A solar eclipse recorded in Assyrian chronicles, for instance, has been definitively linked by modern calculations to a specific date in the year 763 BC. This single celestial event provides a fixed point, a peg in time that historians and archaeologists use to verify the timelines of entire empires, correlating the reigns of kings with the predictable motions of the solar system. What does this journey from terror to triumph reveal? It shows that our relationship with nature's most dramatic displays has always been a powerful catalyst, first for story and ritual, and ultimately for a deeper understanding of the universe's immutable laws. The human reaction to an eclipse is a mirror, reflecting our enduring need to find order in the apparent chaos of the cosmos. This same search for order would next be applied to the steady, wandering lights we call the planets. The steady wanderers of the night sky presented an ancient puzzle that refused to be solved with simple stories. Planets like Mars and Venus did not follow the predictable, circular paths of the fixed stars. Instead, they would slow down, stop, and reverse course in a baffling loop known as retrograde motion before resuming their journey. This celestial dance challenged the very idea of a perfect, orderly heaven and demanded an explanation. The Babylonians tackled this mystery not with grand theories, but with relentless data collection. Over centuries, their scribes compiled ephemerides, intricate clay tablets that functioned as predictive almanacs. These tables forecast the future positions of planets with remarkable accuracy, using mathematical schemes built from generations of past observations. They were not concerned with why the planets moved this way, but with precisely how they would move, creating a practical, computational science of the heavens. This vast archive, as historian Alexander Jones notes, represents a profound shift from seeing planets as mere divine messengers to treating them as objects whose motion could be described and even predicted by mathematics. Greek thinkers later inherited this data and wrestled with its implications, attempting to build a physical model of the cosmos to explain the strange retrograde loops. Ptolemy, working in Alexandria in the 2nd century, synthesized these ideas into an incredibly complex geocentric system. His model used a series of circles upon circles, called epicycles and deferents, to mathematically mimic the planet's observed path. While fundamentally incorrect, it was a brilliant and powerful computational tool that could predict planetary positions for centuries, and its influence would shape astronomical thought for over 1,000 years. This intellectual journey was not confined to the Old World. Across the Atlantic, Maya astronomer priests achieved a similar feat through dedicated observation. They calculated the 584-day synodic cycle of Venus with such precision that they could predict its dramatic transformations from the morning star to the evening star and back again. These appearances were woven into their sacred calendar, dictating the timing of ceremonies and even the planning of military campaigns, demonstrating a sophisticated understanding that emerged entirely independently. The tracking of these planetary cycles was aided by increasingly sophisticated tools. In the medieval Islamic world, scholars refined the astrolabe, an intricate handheld computer of brass and star maps that could solve the problems of time and celestial position. It allowed an observer to measure the altitude of a planet and track its changing place against the fixed stars, turning the sky into a measurable, navigable space. This global, multi-millennia effort to understand planetary motion, from Babylonian arithmetic to Ptolemaic geometry, laid the essential groundwork for all of modern astrophysics. It established the crucial practice of long-term observation, the belief that the universe operates by consistent rules, and the mathematical language needed to describe those rules. The patience required to see these slow celestial cycles repeat over a human lifetime, let alone over centuries, is a powerful reminder that some truths about the cosmos can only be revealed to those who watch and wait. This deep engagement with the wandering stars ultimately forces our gaze to their fixed counterparts, the timeless constellations that provided the stable canvas for this entire cosmic drama. Against the steady wanderers, the fixed stars provided a timeless canvas of familiar patterns. Ancient cultures across the world did not merely see random dots of light. They connected them into constellations, weaving the cosmos into a grand tapestry of myth and meaning. These star patterns were humanity's first maps of the heavens, serving as essential tools for memory, navigation, and cultural storytelling. The Greek hero Orion, forever pursuing the Pleiades across the sky, or the Chinese asterisms depicting the entire imperial court with its officials and chariots, were more than just entertaining tales. They were sophisticated mnemonic systems, turning the overwhelming vastness of the night into a recognizable and memorable storybook. This celestial storytelling was a global phenomenon, meticulously recorded in different ways. In the 2nd century, the Greek-Egyptian scholar Ptolemy compiled his star catalogue, the Almagest, systematically listing over 1,000 stars and 48 constellations, a work that would define Western astronomy for over a millennium. Simultaneously, indigenous cultures preserved their own detailed sky maps through vibrant oral traditions, where the Milky Way might be a river of spirits or a path of ashes, and where every star cluster held a story of ancestral beings or animal guides. As astrophysicist Bradley Schieffer has observed, the specific myths attached to these constellations were deeply reflective of local environments and societal values. The Inuit, living in a world defined by snow and ice, saw the Pleiades not as 7 sisters, but as a team of dog sleds. The Babylonian constellations, intimately tied to their pantheon of gods, directly shaped the 12 signs of the Western zodiac that persist today. These patterns had profoundly practical applications. A farmer in ancient Mesopotamia knew to begin the harvest when the star cluster we call the Pleiades rose just before dawn. A Polynesian navigator steering a canoe across the open ocean would steer by the rising point of specific constellations like the Southern Cross. This knowledge was encoded into art and architecture for preservation. The ceilings of Egyptian tombs were painted with precise star charts to guide the soul to the afterlife. Navajo healers created intricate sand paintings that mirrored celestial patterns, using them in ceremonies to restore harmony between the individual and the cosmos. Consider the Great Bear, Ursa Major, a constellation recognized across the Northern Hemisphere. In many Native American traditions, its movement through the sky throughout the year signaled the changing seasons, its position telling people when to hunt, when to gather certain plants, and when to prepare for winter. This was more than simple observation. It was intergenerational learning, where elders used the story of the celestial bear to impart crucial ecological awareness to the young. What does this incredible diversity of star lore ultimately reveal? It shows a universal human creativity, a shared drive to impose order on the apparent chaos of the universe by telling stories. We see our own lives, our struggles, our families, and our environments reflected in the stars above. This foundational practice of mapping the sky with narrative required not just imagination, but also increasingly sophisticated tools to measure and record the very motions these stories sought to explain. These instruments were the physical embodiment of a celestial obsession, the tangible tools that turned wonder into measurement. To track the sun's path, Egyptian astronomers used the Merkit, a simple forked sight made from a palm rib and a plumb line. With it, a priest could align a star with remarkable precision, marking its transit across the night sky. This was paired with the bay, a notched palm rib that functioned as a ruler, transforming the heavens into a measurable grid. Their days were marked by shadow clocks, the earliest known sundials, which divided daylight into defined hours by tracking the movement of a simple gnommon's shadow. This was practical science in its purest form, born from the need to time religious ceremonies and coordinate the labor that sustained the kingdom. The Greeks later refined these ideas into breathtakingly complex models. The Armillary Sphere, a series of interlocking bronze rings representing the celestial equator, the ecliptic, and other key circles, was a portable cosmos one could hold in their hands. It allowed a scholar to visualize and calculate the positions of celestial bodies, a three-dimensional map of the universe that remained a cornerstone of astronomical education for centuries. But perhaps the most astonishing find is the Antikythera Mechanism. Recovered from an ancient shipwreck, this corroded bronze device is now understood to be an intricate analog computer. Using a system of over 30 precision gears, it could predict the positions of the sun and moon, model the phases of the moon, and even forecast eclipses. It likely showed the motions of the planets, a mechanical simulation of the cosmos that reveals a level of technological sophistication we never imagined for its time. Modern reconstructions, like those by historian Tony Freeth, show a device of breathtaking ingenuity where turning a hand crank would advance the celestial display through years, even decades. This was not just a tool for prediction, it was a philosophical statement, a working model of a universe governed by mechanical law. Across the Atlantic, Mayan astronomers developed their own unique architectural instruments. At sites like Chichen Itza, they constructed zenith tubes, vertical shafts within buildings that were aligned to capture a beam of sunlight only on the days the sun passed directly overhead. This precise event marked the key dates for planting maize, linking the cosmos directly to the sustenance of life. The caracol, with its narrow, strategically placed windows, served as a permanent observatory for tracking the path of Venus, a planet central to their cosmology and warfare. These structures were not built in isolation. In Britain, the great stones of Stonehenge were erected over generations, their massive lintels and trilithons forming a permanent frame for the sun at the solstices. As archaeoastronomer Clive Ruggles has demonstrated, the geometry of the site captures the solar extremes with a consistency that speaks to centuries of accumulated knowledge. Similarly, in the high Andes, the Chanquillo Towers in Peru form an artificial horizon, their 13 spines lining up with the sun's rising position throughout the year, a solar calendar carved into the landscape itself. The construction of these sites was a monumental undertaking. Stonehenge required the transport of bluestones from over 150 miles away, a feat of engineering and social organization that reveals just how critical celestial order was to these communities. In China, astronomers cast elaborate bronze armillary spheres, while in the Islamic world, the Great Samarkand Observatory housed a massive sextant fixed into the ground, allowing for unprecedented accuracy in measuring star positions. The individuals who operated these tools were often priests or court scholars, holding a unique position at the intersection of science, spirituality, and state power. Their ability to read the sky and predict celestial events was a source of immense authority. A Babylonian priest who could forecast an eclipse, or a Mayan daykeeper who knew the precise return of Venus, was not just an astronomer, but a mediator between the people and the divine. Their knowledge was often guarded, passed down through strict lineages or within temple schools. The design of these instruments and observatories teaches us a profound lesson about the ancient mind. There was no separation between the artist, the engineer, and the priest. The beauty of a bronze sphere, the imposing grandeur of a stone circle, and the spiritual significance of a celestial event were all part of a single, unified pursuit of cosmic order. This deep integration of science, art, and spirituality challenges our modern categories, reminding us that the drive to understand the stars has always been a fundamentally human endeavor, one that seeks to find meaning as much as it seeks to measure. Behind these instruments and observatories were the brilliant minds who gave them purpose. Men like Hipparchus of Rhodes, working in the 2nd century BC, were not content with just watching the stars. They sought to measure and define the heavens with mathematical rigor. Using little more than a dioptra, a simple sighting tube, he meticulously charted the positions and brightness of over 850 stars, creating a catalogue of such precision that it would become the foundation for Ptolemy's Almagest centuries later. It was Hipparchus who noticed a subtle shift in the sky over time, a slow wobble in the Earth's axis we now call precession, which causes the celestial poles to trace a circle over 26,000 years. This was a discovery of staggering insight, revealing a cosmos in slow, constant motion long before the invention of the telescope. Across the world in Han Dynasty China, Zhang Heng served as the court astronomer, a role that combined the duties of chief scientist, engineer, and imperial advisor. He improved the Armillary Sphere, creating a water-driven model that simulated celestial motions, and he advanced theories on the causes of solar and lunar eclipses, correctly identifying the shadows cast by heavenly bodies. His famous seismoscope, a bronze vessel with dragons and frogs, could detect distant earthquakes, demonstrating a mind that saw interconnected patterns in the natural world, from the tremors of the earth to the rhythms of the sky. These individuals were often supported by powerful institutions. In Babylon, a scholar named Kidanu led efforts to refine the lunar theory, using centuries of data to perfect predictions of the moon's motion, his work so accurate that it defined the Babylonian calendar. In the Mayan world, anonymous scribes, working under the patronage of kings, painstakingly painted astronomical data into codices like the Dresden Codex, encoding the complex cycles of Venus with a precision that served both prophecy and statecraft. They were scientists, priests, and philosophers all at once, their roles seamlessly blended in a world that saw no divide between the spiritual and the physical cosmos. Historian James Evans notes that their contributions formed a cumulative, cross-cultural tradition. Knowledge from Mesopotamia flowed to Greece. Greek texts were preserved and expanded by Islamic scholars in Baghdad and Damascus, and Indian astronomical texts like the Surya Siddhanta, which detailed planetary orbits and eclipses, influenced thinkers across Asia. Sometimes ideas emerged that were centuries ahead of their time. In 5th century India, the brilliant mathematician Aryabhatta proposed a model of the solar system in which the Earth spun on its axis and the planets revolved around the Sun, a heliocentric concept that would not gain acceptance in the West for another 1,000 years. His work, along with that of figures like the Greek Aristarchus of Samos, shows how flashes of profound insight could appear independently, only to be lost and later rediscovered. What drove these individuals to dedicate their lives to this meticulous, lifelong pursuit? Without modern technology, their work required immense patience, often observing the same celestial cycles for decades to gather enough data to confirm a single pattern. They faced the challenges of their era, from political instability to the simple physical difficulty of observing night after night. Their legacy, preserved in fragile papyri, clay tablets, and painted books, is a testament to a universal human drive, not just to predict, but to truly comprehend our place in the universe. Their stories remind us that the pursuit of knowledge is a long conversation across the centuries, where every observation, no matter how ancient, adds a vital piece to an infinite puzzle. This profound human endeavor was always shaped by the rich and varied cultural soil from which it grew. The sky was never a neutral canvas for ancient observers. Its patterns were a sacred script read by priests and rulers who held the keys to its meaning. In Egypt, the pharaoh was not just a king, he was the living embodiment of the sun god Ra, a divine intermediary whose power was reaffirmed by the very architecture of the state. Temples were precisely aligned so that the sun's rays would pierce the inner sanctum on the morning of the solstice, bathing the god's statue in light and proving the pharaoh's unbreakable bond with the cosmic order. This was astronomy as political theater, a celestial endorsement of authority carved in stone. Similarly, in Mesopotamia, no king would declare war or enact a new law without first consulting the celestial omens. Priests serving as the state's chief scientists scanned the night for any anomaly. A lunar eclipse might signal the illness of a monarch, while the path of a planet through a certain constellation could foretell the success of a harvest. The detailed astronomical diaries they kept were not for academic curiosity. They were essential tools of governance, the intelligence reports of a civilization that believed its fate was written in the stars. This deep entanglement of cosmos and culture is a global story. As historian David Pingree has explored, every society viewed the heavens through the lens of its own cosmology. For the Norse, the world tree Yggdrasil held the 9 realms in its branches, with the stars as embers from Muspelheim. For Aboriginal Australians, the Dreamtime was not a past event but an eternal reality playing out in the constellations overhead, where every dark cloud in the Milky Way was an ancestral being. These were not just charming stories, they were complete worldviews that dictated what people saw and, crucially, what they recorded. A celestial event that fit the mythic narrative was noteworthy, one that might be forgotten or reinterpreted. This cultural lens shaped the very practice of observation. We see this profound connection in the great public festivals tied to celestial cycles. The Inca Empire celebrated Inti Raymi, the festival of the sun, at the winter solstice. This was a moment of communal renewal where offerings were made to plead for the sun's return, and the emperor demonstrated his unique role in maintaining the balance of the world. In Babylon, the New Year festival, Akitu, was timed with the spring equinox. During this 12-day celebration, the king would undergo a ritual humiliation before the statue of the god Marduk, then be reinstated to his throne. This reenactment of the creation myth, synchronized with the sun's renewal of the year, was believed to regenerate cosmic and social harmony. The entire community participated in a drama that linked the rhythm of the sky directly to the health of the state and the legitimacy of its ruler. Even the most frightening celestial events were tamed by myth. An eclipse was not a random alignment, it was a dragon swallowing the sun in China, or the wolf skull chasing the sun chariot in Norse legend. These stories provided a framework for understanding, transforming a moment of primal terror into a narrative with a known beginning, middle, and end. They offered comfort, suggesting that even chaos had its place within a larger, divine order, and prescribed a ritual response like banging pots or making sacrifices to help restore the natural balance. Recognizing this rich cultural and religious context forces us to reconsider the ancient records we so highly prize. Their value is not merely in their raw data, but in the profound human needs they represent, the need for order, meaning, and connection to a power greater than ourselves. This perspective also invites a humbling reflection on our own time. Is modern science, with its quest for pure objectivity, entirely free from the cultural soil in which it grows? Our own theories of the universe's beginning, from the Big Bang to multiverses, are shaped by the questions our era deems important and the tools our culture has built to ask them. The ancient stargazers remind us that we always observe the universe from a particular place, both in the galaxy and in the human story. This holistic understanding of their world, where science, spirituality, and power were inextricably linked, now sets the stage for a final, critical question. Just how accurate were these culturally framed observations, and what can their precision teach us about the universal human capacity for discovery? The precision of a Babylonian eclipse prediction, accurate to within hours, feels almost miraculous for its time. Yet for every such triumph, there are celestial records tinged with mythology or slight observational error. How do we sift the scientific gold from the cultural filter? The answer lies in a modern detective story where astronomers like F. Richard Stephenson use statistical analysis to compare ancient descriptions with computer models that can retrocalculate the past night sky. This rigorous cross-checking reveals a fascinating spectrum of accuracy. Cataclysmic events like supernova were often recorded with stunning timeliness, sometimes within days of their first visible light, because their sudden, brilliant appearance was impossible to ignore. The positions of planets, however, could be more approximate, as their steady wanderings required more nuanced long-term tracking. The very tools that enabled this knowledge also imposed limits. Observing with the naked eye meant that atmospheric haze, a passing cloud, or simple human fatigue could introduce small but significant errors into a measurement. A scribe copying a record might inadvertently transpose a number, and the deep cultural belief that a comet was an omen could lead an observer to emphasize its supposed meaning over its precise astronomical path. The Chinese records of sunspots are a perfect example of this trade-off. Their meticulous, state-sponsored observations provide an invaluable 1,000-year history of solar activity for modern physicists. Yet because their primary focus was on interpreting these spots as celestial warnings to the emperor, they may have overlooked more routine, less politically charged solar phenomena. What was deemed noteworthy was always shaped by the cultural lens. A civilization might record a rare eclipse with fervent detail while ignoring the steady, predictable phases of the moon, simply because one was an omen and the other was background rhythm. This does not diminish their achievement, it humanizes it. Their commitment was not to our modern idea of pure objectivity, but to a truth that intertwined measurement with meaning. The incredible consistency found when comparing, for instance, Babylonian, Chinese, and Maya eclipse records reveals a shared global dedication to capturing the realities of the cosmos, each through their own unique window. This critical evaluation of their strengths and weaknesses offers a profound lesson about the nature of science itself. Progress is not a straight line from myth to fact, but a slow, collaborative process of refinement, where every generation builds upon the observations of the last, correcting some errors and introducing new ones, all while striving for a clearer picture. Our own scientific models will one day be seen as limited by the tools and cultural assumptions of our age. The recovery of this lost knowledge, therefore, is not just about filling in historical gaps, it is about understanding the very engine of discovery. And this entire endeavor rests on a fragile thread, the miracle that any of these records survived the ravages of time at all, setting the stage for the next great challenge, their preservation and transmission across the centuries. The survival of these celestial records is a story of both fragility and incredible endurance. Long before digital backups, knowledge was etched onto the most durable materials available, from Mesopotamian clay tablets baked hard in the sun to Egyptian papyrus scrolls stored in dry tombs and stone inscriptions carved into temple walls across the ancient world. This physical resilience was matched by the dedication of countless scribes and astronomers who meticulously copied and recopied texts, generation after generation, often within the protected walls of monasteries or royal libraries. These scholarly networks became the lifeblood of astronomy, ensuring that crucial works could travel and be preserved even when empires fell. The journey of Ptolemy's Almagest is a perfect example. Its original Greek version was housed in the legendary Library of Alexandria, a repository of ancient wisdom. When that library was lost, the text survived through Arabic translations made by scholars in Baghdad's House of Wisdom during the Islamic Golden Age. These translations were later rendered into Latin, bringing the work back to Europe and fueling the scientific revolution centuries later. This was not an isolated event. It was part of a vast intercultural exchange where ideas flowed along trade routes. Indian astronomical texts with their advanced mathematics were translated and absorbed by Islamic scholars, who then refined and expanded upon them, creating new star catalogues and instruments that would later influence the West. Yet this transmission was perilous. The same Spanish conquest that brought Mayan codices to European attention also led to the destruction of countless others, seen as pagan objects. Only a handful, like the Dresden Codex, survived by chance in distant libraries, their complex Venus tables waiting centuries for someone to understand their language. Historians like Owen Gingerich have dedicated their careers to tracing these improbable journeys, mapping how a single idea could travel from Babylon to Greece, to India, to Persia, and finally to Renaissance Europe. The loss of knowledge was often catastrophic. The burning of the Library of Alexandria is the most famous example, but countless other archives have been lost to fire, war, or simply the slow decay of time, leaving immense gaps in our historical sky charts. Today, we are recovering some of that lost data through remarkable technologies. Multispectral imaging, for instance, can see through the stains and fading on ancient papyrus or palimpsests, revealing observations that were invisible to the naked eye for 1,000 years. The painstaking excavation of Babylonian sites continues to yield new caches of tablets. When these are deciphered, they provide stunning insights, like the precise lunar theory developed by scholars like Kidanu, which allowed them to predict the moon's motion with mathematical elegance. This entire epic of preservation, from the steady hand of a scribe to the advanced imaging of a modern lab, highlights a profound truth about human curiosity. It is a flame that can be dampened but never fully extinguished. It forces us to ask a vital question for our own era. As we store our scientific data on servers and in the cloud, what are we doing to ensure that our own records will be readable and resilient in 1,000 years? The enduring legacy of these ancient observers now finds new purpose as their millennia-old data is applied to some of the most pressing questions in modern astrophysics. These ancient observations are now active participants in modern astrophysics, providing data on a timescale no single human life can encompass. The meticulous records of Babylonian eclipse timings, for instance, have become a key to unlocking a subtle celestial dance. By comparing the expected time of an ancient eclipse with the moment it was actually observed, scientists can measure the gradual slowing of Earth's rotation and the moon's incremental drift away from our planet. This tiny discrepancy, measured over millennia, confirms the long-term effects of tidal forces, a slow-motion process only visible with the benefit of ancient records. Similarly, the continuous logs of Chinese sunspot observations provide a 1,000-year baseline of solar activity. When cross-referenced with climate data from ice cores and tree rings, these records reveal how periods of low sunspot activity, like the Maunder minimum, often coincided with periods of global cooling, linking the sun's mood swings directly to Earth's historical climate. This is not just historical curiosity, it is vital longitudinal science. As NASA scientist Donald Yeomans has emphasized, these accounts are our only window onto transient cosmic events that occurred before the invention of the telescope. The sudden appearance and slow fade of a supernova, so carefully noted by Song Dynasty astronomers, gives us the precise birth date of the Crab Nebula. Modern telescopes can then study this expanding cloud, measuring its rate of growth and energy output to test and refine our models of stellar evolution. Without that ancient timestamp, the Crab Nebula would be just another beautiful mystery, its story of catastrophic birth lost to time. The same principle applies to comets. Detailed descriptions of a comet's path and tail from Chinese and Korean annals allow astronomers to calculate its past orbits with incredible precision, tracing its history through the inner solar system and understanding how its path is gently perturbed by planetary gravity over centuries. This historical data is so valuable that it even helps in archaeology. A solar eclipse mentioned in an Assyrian chronicle can pin an entire dynasty to an exact year, while the celestial alignment of a Mayan temple doorway can confirm the precise purpose of a structure, bridging the gap between the stars and the stones left behind. This practical utility raises a profound ethical question for our time. As we continue to mine these ancient sources, how do we ensure we are interpreting them within their own cultural context, rather than simply stripping them for raw data? The records were never meant to be mere numbers in a spreadsheet. They were narratives imbued with meaning. The true value lies in honoring both the scientific measurement and the human story behind it, recognizing that our quest to understand the cosmos is a continuous thread woven through every generation. This legacy of looking up challenges us to see our own scientific endeavors as part of a much longer conversation, one that began when the first human wondered at a strange new light in the heavens. Those ancient star charts and stone observatories were never just about tracking time. They were profound philosophical statements about humanity's place in the cosmos. The Stoic philosophers of ancient Greece envisioned a universe bound by a divine, rational order, a cosmic harmony where human virtue lay in aligning one's life with the celestial rhythm. This search for a grand, unifying principle finds a powerful parallel halfway across the world in the Mayan understanding of cyclical time, where history itself was not a linear march but a series of repeating patterns and renewals. Both perspectives, though separated by vast oceans, confronted the same existential questions that we still grapple with today. Is the universe a chaotic void or a place of inherent order and meaning? Are we merely inhabitants of a planet or active participants in a cosmic story? These early civilizations answered with a resounding belief in a connected, meaningful cosmos, a vision that challenges the sometimes cold, impersonal narrative of modern science. Their approach forces a humbling realization that our current models of the universe, for all their technological sophistication, are simply the latest chapter in an age-old human conversation about the nature of reality itself. We have not necessarily discovered new questions, we have simply developed new languages for asking them. This is where the work of ethicists like Lorraine Daston becomes so vital. She reminds us that all knowledge, including our own, is culturally constructed. The meticulous data of the Babylonians was framed by their belief in celestial omens, just as our own astrophysics is shaped by a culture that values mathematical abstraction and empirical proof. Recognizing this does not diminish the power of science, it enriches it, fostering a necessary cultural humility. It asks us to see indigenous oral histories not as primitive myths, but as sophisticated, alternative ways of knowing that hold intrinsic value. The Polynesian art of wayfinding, for instance, is a profound science of ecology and interdependence, where navigating by the stars requires a deep, respectful relationship with the ocean, the winds, and the wildlife. This stands in stark contrast to a modern, tech-driven approach that can sometimes view the cosmos as a mere resource to be conquered or consumed. How might this ancient wisdom inform our own era of space exploration? The ethical duty extends beyond simply preserving these records in museums. It calls for honoring them without appropriation, listening to the philosophical insights they offer about sustainable practice, and our responsibility to the cosmic environment we are only beginning to explore. The real challenge for our time is to integrate this reflective wisdom, to build a future where our advanced telescopes and satellites are guided not only by curiosity, but by the same reverence for cosmic harmony that inspired the builders of Stonehenge and the Star Watchers of Babylon. This reflective journey through humanity's celestial past naturally brings us to a point where we must clear away the fog of common misunderstanding and confront the myths that have grown around these ancient astronomers. A lingering question haunts our appreciation of these ancient builders. Could they have accomplished such feats entirely on their own, or does the true explanation lie with visitors from the stars? This idea of ancient astronauts, while captivating, often overlooks the profound evidence of human ingenuity we have just explored. The Mayan calendar, for instance, did not require alien supercomputers. Its breathtaking accuracy was born from generations of patient observation and a sophisticated mathematical system they developed themselves, visible in the incremental calculations preserved on their own bark paper codices. Scholars like Jason Colavito point out that these myths, however entertaining, can subtly undermine the capabilities of early cultures, suggesting they were incapable of the very innovations that defined them. The archaeological record tells a different story, one of gradual mastery. We possess Babylonian clay tablets that show step-by-step astronomical calculations, revealing how complex predictions were built from simpler observations over centuries. This was not a sudden gift of knowledge, it was a hard-won human achievement. Consider the celestial alignments of monuments like the pyramids or Stonehenge. The precision did not appear overnight. It was the result of long-term observation and a process of trial and error, refined over many generations. There is a complete absence of any credible evidence for extraterrestrial influence within the historical texts and art of these civilizations. When they depicted the gods, they described them in human or animal forms, not as pilots of advanced spacecraft. A powerful example is found in the Nazca lines of Peru. These vast geoglyphs etched into the desert floor were once speculated to be alien runways or landing strips. Modern archaeological study, however, reveals a much more plausible and culturally rich explanation. They were ritual pathways carefully aligned with celestial events like the solstice sun and used in ceremonies related to water and fertility. Their creation was well within the scope of the Nazca people's known technology and organizational skills. This demonstrates how science and culture intertwine in entirely human ways. So why do these fantastical explanations persist? They often fill gaps in our own understanding with dramatic stories, offering simple answers to complex human achievements. The true challenge and the greater reward is to foster a deeper appreciation for the actual innovations. It is more awe-inspiring to recognize that people using simple tools, keen observation, and shared knowledge over generations could map the heavens and raise monuments to last for millennia. This clarity about our human past, free from unsubstantiated claims, allows us to see the direct line connecting their celestial records to the stories we tell today. That celestial dialogue between past and present did not end with the last clay tablet or star chart. It echoes powerfully in our modern culture, where ancient astronomical records find new life in the stories we tell and the art we create. The doomsday prophecies linked to the Mayan calendar's cycle endings are a prime example, transforming a sophisticated system of cyclical time into a global media spectacle. While this popular interpretation was a dramatic misunderstanding, it ignited worldwide curiosity about Mayan civilization and its profound connection to the cosmos, demonstrating how ancient ideas can be reshaped to fit contemporary anxieties. Similarly, the myths born under Greek skies continue to fuel our imagination. The constellations named for their heroes and monsters are now the familiar settings for epic science fiction sagas, where starships bear the names of ancient gods and celestial lore provides a foundational language for exploring new worlds. This enduring appeal is not accidental. It taps into a deep, shared human need to find narrative in the night sky, to see our own struggles and adventures reflected in the stars above. Visionaries like Carl Sagan masterfully wove these threads together in his series Cosmos, presenting the work of ancient astronomers not as dusty history, but as the first thrilling chapters in humanity's greatest adventure. He framed figures like Eratosthenes and Hipparchus as pioneers, their curiosity a direct ancestor to our own, thereby inspiring countless viewers to look up with a renewed sense of wonder. This educational bridge is strengthened by institutions like museums and planetariums, where visitors can stand beside full-scale replicas of Stonehenge's pillars or operate a model of an armillary sphere, turning abstract concepts into tangible experiences. The cultural absorption of this celestial heritage is everywhere. Children's books retell the story of Orion the Hunter, board games are built around navigating by the stars, and fashion designers draw inspiration from the intricate patterns of star maps. Even the breathtaking images from the Hubble Space Telescope often evoke direct comparisons to ancient descriptions of cloudy, celestial forms, creating a visceral link between the unaided eye observations of the past and our technologically enhanced vision of the present. This cultural resonance presents a unique opportunity. How can we leverage this widespread fascination to foster genuine scientific literacy and ensure the preservation of historical knowledge? The answer may lie in the very technology that defines our age. Digital archives are now safeguarding fragile manuscripts from further decay, while virtual reality can transport students inside a reconstructed Babylonian observatory, allowing them to witness a predicted eclipse just as the ancient priests did. The dialogue is no longer one-way. Modern algorithms can scan thousands of digitized cuneiform tablets, searching for forgotten celestial references that might reveal a lost supernova or a previously unknown comet sighting. This fusion of cutting-edge technology and ancient wisdom promises to unlock new chapters in a story that began millennia ago, ensuring that the legacy of those first sky watchers continues to inform and inspire our journey into the cosmic ocean. A Babylonian clay tablet, once thought to contain simple administrative text, was recently scanned in 3 dimensions. This high-resolution digital model revealed something astonishing: a complex geometric diagram used to calculate the position of Jupiter. The mathematics was so advanced it demonstrated a level of sophistication we never knew the Babylonians possessed, all uncovered because a modern scanner could see the subtle impressions of the scribe's stylus. This is the new frontier of ancient astronomy, where technology is not just assisting research, it is fundamentally rewriting history. Digital imaging is at the forefront of this revolution. Multispectral imaging, for instance, uses different wavelengths of light to see through stains and faded ink on documents that have been unreadable for centuries. The Archimedes palimpsest, a prayer book made from scraped clean parchment, was one such breakthrough. When scientists scanned its pages, they recovered not only the original works of Archimedes, but also previously unknown astronomical commentaries, notes that had been hidden in plain sight for nearly 1,000 years. This technology is now being applied to charred scrolls from Herculaneum, papyri from Egyptian tombs, and Mayan codices, revealing star charts and planetary observations we never knew existed. Beyond the text itself, satellite data and aerial surveys are expanding our understanding of ancient observatories. LIDAR technology, which uses laser pulses to map the ground through dense jungle canopy, has uncovered entire networks of ceremonial sites and structures aligned with celestial events. In the jungles of Central America, LIDAR has revealed hidden platforms and building complexes that were precisely oriented to track the solstices or the path of Venus. We are no longer limited to what we can see from the ground. We can now map the intentionality of an entire landscape, showing how widespread and sophisticated sky watching truly was. The sheer volume of data from these discoveries is immense, but artificial intelligence is stepping in to help. Machine learning algorithms are being trained to recognize and translate cuneiform symbols or hieroglyphic texts at a speed no human team could ever match. Researchers like Alexander Jones are building vast digital databases that compile astronomical records from across the globe, from Babylonian clay to Chinese silk. By cross-referencing these millions of data points, algorithms can identify patterns, spot rare events recorded in multiple cultures, and even detect subtle errors made by scribes, which in turn helps historians understand how knowledge was copied and transmitted across generations. To ensure the authenticity of these records, scientists turn to radiocarbon dating, a technique that measures the decay of carbon-14 in organic materials like papyrus or leather. This process provides an independent clock, verifying that a document describing a comet really does come from the era when that comet was seen. It anchors the historical record in physical reality, separating genuine observations from later copies or forgeries. This global effort is not confined to university labs. Citizen science projects now allow anyone with an internet connection to contribute. Online platforms invite the public to help transcribe weather records from ship logs or identify constellations in digitized medieval manuscripts, harnessing the power of collective curiosity to process data that would otherwise take decades. This collaborative spirit, however, brings important ethical questions to the surface. As we digitize this cultural heritage, who should have access to it? Institutions are now working closely with indigenous communities to ensure that sacred knowledge is handled with respect and that digitization does not become a form of digital exploitation. The goal is to create open access archives that serve global scholarship while honoring the cultural origins of the knowledge. The potential of these tools is boundless. What other lost observations of supernova are waiting to be found beneath the surface of a palimpsest? How many more celestial calendars are hidden beneath the jungle floor? These technologies are democratizing access to the past, transforming ancient astronomy from a niche academic field into a living, evolving story that we can all help to uncover. This digital bridge to the past does more than just satisfy curiosity. It opens a direct channel for education, inviting a new generation to look up at the night sky with the same sense of wonder that moved the ancients. These ancient records are finding a vibrant new life far beyond museum archives, actively shaping how we learn. In classrooms around the world, the meticulous data of Babylonian scribes and the architectural genius of Mayan builders are becoming powerful tools to teach not just astronomy, but history, mathematics, and critical thinking. Imagine students not just reading about ancient Egypt, but reconstructing their civil calendar by tracking the heliacal rising of Sirius with a simple star chart. Or a mathematics class calculating the Saros cycle to predict the next lunar eclipse, using the same geometric principles discovered millennia ago. This hands-on approach transforms abstract dates and numbers into a tangible, human story of discovery. Programs like NASA Ancient Observatories Initiative champion this method, showcasing how cultures from every continent looked up and contributed to our understanding of the cosmos. This perspective naturally fosters a more inclusive and globally aware view of science, where every civilization has a voice in the grand conversation. Educators and advocates like Emily Lakdawalla emphasize the profound impact of building a physical model of an armillary sphere or decoding the celestial symbols in a Navajo sand painting. These projects make complex concepts accessible, but more importantly, they highlight the human curiosity that drives all scientific inquiry. The integration of indigenous knowledge is particularly transformative for modern STEM curricula. When students learn how Polynesian navigators crossed thousands of miles of open ocean using only the stars, wind, and waves, it teaches a profound lesson in ecological interdependence and observational science that no textbook alone can provide. Technology is amplifying these lessons, with virtual reality now allowing a student in a classroom to stand virtually within the Caracol Observatory at Chichen Itza and watch Venus set through its ancient viewing slit. Public engagement extends into digital spaces, where YouTube channels and online lectures translate academic findings into gripping narratives for a global audience, effectively dismantling the walls between the university and the public square. Consider a classroom project that compares Chinese and Babylonian records of the same solar eclipse. Students must analyze different writing systems, calendars, and cultural interpretations of the event, learning data analysis and historical methodology while celebrating the diversity of human response to the same cosmic spectacle. This does more than teach facts, it builds bridges of understanding. So how do we expand these vital educational efforts? The challenge is to weave this ancient wisdom into the very fabric of learning, from primary school to lifelong education, ensuring it is not an occasional topic but a foundational perspective. We must create curricula that honor these diverse ways of knowing, showing that the drive to understand the universe is a universal human trait. This focus on inspiring the next generation through the lessons of the past makes one thing undeniably clear: the urgent need to safeguard this irreplaceable knowledge for the future. Safeguarding these fragile records is a race against time and the elements. The very clay tablets and papyrus scrolls that have survived for millennia now face unprecedented threats from a changing climate, with rising humidity levels threatening to erase ancient ink, and from the tragic destruction of heritage sites in regions of conflict. The loss is not just of objects, but of entire chapters in humanity's collective memory. In response, a global alliance of archaeologists, librarians, and technologists is mounting a digital defense. Initiatives like the Digital Babylonian Library are creating high-resolution, three-dimensional scans of every known cuneiform tablet, making them freely available online for anyone in the world to study. Simultaneously, the Endangered Archives program ventures into remote areas to digitize fragile manuscripts before they can be lost to neglect or environmental hardship. This digital migration is more than just creating a backup. It is a form of democratization, ensuring that a student in a small village has the same access to a 5,000-year-old star chart as a professor at a major university. These preservation efforts extend beyond texts to the monumental observatories themselves. UNESCO World Heritage designations now protect sites like Stonehenge and the 13 Towers of Chanquillo in Peru, recognizing them not merely as ancient ruins but as foundational landmarks of human scientific achievement. This international framework helps shield them from inappropriate development and provides resources for their careful conservation. The philosophy driving this work, as championed by thinkers like Kathleen Singe-Moritz, is inherently interdisciplinary. It requires data scientists to build the robust digital architectures that will house this knowledge for centuries, archaeologists to provide cultural context, and ethicists to ensure that preservation respects cultural sovereignty and does not become a new form of exploitation. Innovative methods are emerging to meet the scale of the challenge. Crowdsourcing projects invite the global public to help transcribe thousands of weather records from old ship logs or identify constellations in medieval manuscripts, turning a monumental task into a collaborative human effort. Some archivists are even exploring the potential of blockchain technology to create an unalterable chain of custody for digital copies, verifying their authenticity for future scholars and protecting against misinformation. Yet the most vital element is often the most local. True preservation means keeping knowledge alive within the communities where it originated. This involves storing the sole surviving Mayan codices in state-of-the-art, humidity-controlled facilities, while also partnering with local schools in Central America to develop educational programs that reconnect youth with the astronomical practices of their ancestors. The goal is not to lock wisdom away in a vault, but to revive it as a living tradition. This entire endeavor forces us to confront a profound responsibility. What do we owe to the next 1,000 years? Our duty is to be good ancestors, to use every tool at our disposal, from the simplest community workshop to the most advanced digital ledger, to ensure that the celestial legacy entrusted to us is passed on, not just as data, but as a vibrant and equitable inheritance for all of humanity. Our journey through these ancient records reveals a timeless truth, that the human drive to understand the cosmos is a story written in starlight across every culture. From the Babylonian priests who calculated eclipses to the Mayan astronomers who tracked Venus with breathtaking precision, these early efforts were more than just data collection. They were the very foundation upon which modern astronomy was built. This shared legacy of curiosity and perseverance shows us that the questions we ask today are part of a conversation that has been unfolding for thousands of years. The key takeaway is not just the scientific value of these records, but the profound human connections they represent. They remind us of the vital importance of preserving these fragile bridges to our past, whether through digital archives or the protection of sacred sites. They demonstrate the incredible value of diverse perspectives in science, proving that our understanding of the universe is enriched by every culture that has ever looked up in wonder. And perhaps most importantly, they offer enduring lessons in humility, teaching us to approach the vast mysteries of the cosmos with a sense of awe. We can carry this legacy forward by supporting the archaeological research that uncovers new fragments of our celestial history, by engaging with the educational resources that bring this wisdom to new generations, and by simply taking a moment to look up at the night sky ourselves, seeing it with the same fresh eyes as our ancestors. We would love to hear which ancient civilization's astronomy fascinates you most, so please share your thoughts in the comments below. If you enjoyed this celestial adventure, subscribe for more explorations into history's hidden gems. Thank you for joining this journey, and may it inspire you to always seek the